I'm going to do file new data. And let's just make up some fake data for our own edification. So can everybody see that all right? So our variable 1, we're going to have 1. Let's just do it, make it simple. N equals 5. And I'm going to sum those up, right? And this is the situation you guys are talking about, where if we have some missing data, are we okay? Are we okay calculating for respondent number 1? They only answered the first 2 questions. Are we okay calculating the mean for just those 2? Or would we want this to be NA? Right? Would we want this to be missing data? Because if they missed any of them, I want to, and that's not, again, not a, that's a researcher decision that they have to make. There's not a rule that I can give you. I think in most cases, people would say, I'll calculate the mean off of these 2, even if they're missing this 1. Just like in this one, I'll calculate the mean off of these 2. And here I'll calculate the mean off of the 3. And I think that's what most people do, intentionally or not. They might not even be thinking about it when they are calculating. So if we use, if we do transform compute, and if I do, and I just do sum, which is a function that I could find down here, right? I could go down here and find, isn't it sum?
Statistical test or function.
Or all? So here, so I could just do that, and I could say, move that sum up. Same, this will work the same way. So I'm just going to type the word sum. Is this what you guys did? This is how you would sum it up. And then I'm going to do variable 1, comma, variable 2, comma, and variable 3, comma, comma. And in this case, no missing data, right? It calculated the average based on, no, I sum the items. I need to divide by, thank you. Divide by, probably the way that, maybe the way that, if we did it this way. Is it average? Is that what they do, or is it mean? So in that case, it included all, and I could have been a little bit more creative here to get, so these all wouldn't be 1. But of course, this mean is calculated with n equals 2, right? Because there's only, it has nothing for variable 3. So it calculated the mean for just those 2. Where for row number 3, it calculated the mean for all 3 of them. The other way to do that would be to do, and in that case, when you told it specifically to calculate this, add these items together, if it doesn't find one of those items, it says, I don't know what to do. And so I'm going to just give you missing data there. And so as you're working with your items, you need to make sure that if you decide to do mean, you know what it's doing and you're comfortable with that. Or if you're not comfortable with that, sum them up and divide by n, and then understand that you'll have missing data wherever you have any missing data within the data.
Is that the more conservative approach?
That word always makes me a little nervous. Just not that word, but what I don't know if I would think of it as conservative. The approach that probably would the approach that would be most common, I think, would be just to use mean function and calculate the mean. I don't know that that's the most conservative. I think maybe if we think about the word conservative in the same way, the more conservative way to do it might be if they're missing any data across those items, let's exclude them from the summed total or from the average total from the aggregated item. And I think what really matters is by looking at your individual questions and is it okay that can you get rid of one of your questions, take an average on what's left over, and still have the same thing? Does it mean the same thing theoretically as if you calculated the average across all items? And so if it does, if any, if you're comfortable with, this multi-item scale just has 9 items, they're all getting at the same construct, but just slightly different ways. If we get rid of any one of those, I'm not concerned if we're calculating an average on 8 or 7 instead of 9. How much sense does that make? Does it make sense? Does that help, Chris, in terms of, or the other question that was asked? Does that help? Maybe.
No, so I usually do the mean. I'm assuming that's what you do too. So I was assuming that SPSS would have put a number in there, so I wouldn't be able to determine between what's missing and what's not missing. And I couldn't get the other thing to work, so I did it on the items instead of the composite variable.
Which is that's a perfectly fine approach. Had you been able to get SPSS to give you missing data where there was missing data for the items, would have you then used the sum scale or the average scale?
So I didn't know that the computing the variable.
Yeah.
So I had missing data on the items. I didn't
Right.
know that computing the variable would give me the composite variable flex. Right. I couldn't get it to do that.
Right.
Like what it did on your first one.
Right. Right.
So if I could have done that, then yeah, using the variable.
You would have used the because and what if we had, let's say we had 9 items and the person only answered one of the 9 items. I would be uncomfortable calculating a mean for that person based on that one item when everybody else or most everybody else had 9. That's why you just can't, I don't think that you can sort of blindly use one rule or the other. I think you have to think about the context, think about your situation, make a decision that makes sense for you. Then, of course, it's all about making a rational argument for doing that and convincing informed readers that you made the right choice. And to the extent that you can be persuasive, you made the right decision. To the extent that you can't persuade readers, then it becomes problematic. And so, other questions before we move on? I want to review one thing from last week, and then we're gonna actually have another missing data problem that we're gonna work on. Just spend a few minutes working on in class, and then we can put a period on missing data. And then if we get through the other 2 topics that I have in
deck for for week 3, the normality and outliers. If we get through that, we're going to be doing good today. And so, I think we'll be brain dead by the time we get through that. So, if we get to regression, I'm happy to talk about regression. But if we don't get to that till next week, I'm happy with that as well. So, in a couple conversations that I had, and then historically with other students that I have taught over the years, there can be some confusion around the Levene's test and exactly what it is compared to the actual t-test and what it is. Somebody take a stab at, I did the best I could do last week at trying to explain what Levene's test was and what the t-test is. Somebody else take a stab at who thinks they... I think when Levene's test, when we're doing the t-test, it's trying to tell us. Sorry, when we're doing the t-test, we're essentially trying to figure out that there is meaningful difference between my two groups. And the way the t-test runs in SPSS, if I'm fulfilling certain assumptions, such as my variable, my dependent variable is continuous, my independent predictor variable is nominal. The t-test will calculate it. But what about this idea that those two groups do come from two distinct populations? So a Levene's test is almost a precursor to the t-test because it's telling me that these two groups that I'm trying to compare are coming from two distinct populations. Once I've assessed that, I do the t-test to say, okay, they also have meaningful differences between them.
Yeah, and the key is if we were to look at these two rows of the Levene's test and match them up to, or these two columns, and this column with the standard deviations, that is, so the Levene's test is related to, those two columns are related to this column, the standard deviation column. And these two standard deviations are simply the standard deviations for this question, in this case, how the respondent feels towards African Americans. It's the standard deviation for all of those people where we didn't have missing data on income, and their standard deviation is 1.977. And we could use SPSS to calculate that separately. If we didn't trust that this was the right number, we could just do a calculation for standard deviation, making sure we were looking at exactly the same group that SPSS was looking at here. And these very same 417 people would give us this very same standard deviation. And then this other the second standard deviation is for those people who did have missing data on their income variable. That's their standard deviation. Again, we could calculate that using the standard deviation function within SPSS, and we'd come up with this exact same amount, assuming we were telling SPSS only to calculate it on those very same 238 people. And so one of the assumptions of the t-test is that these standard deviations don't vary significantly from each other, that they come from the same population, that one isn't really spread out and the other one is very narrow. And so that's what the Levene's test is testing for us, is just looking at the standard deviation for the outcome variable, for a dependent variable, broken down by, in this case, our two groups. When we do ANOVA, we have the same test, but we have more than two groups in most cases. And so it would be assessing that for 2, 3, or 4, whatever number of groups we have. And so if the F test is significant, which row do we use?
Equal variance is not assumed.
Right. So if this is less than 0.05, we use the equal variance is not assumed. Everybody do that right? There's just a slight correction that researchers have found that if you make this correction, then we don't. If we make this correction, then we're not increasing our likelihood of making an error if we make that correction. And then if this is greater than 0.05, the Levine's test, then we use equal variance as assumed, and we read that t-test, not the t-test below. Does that make sense to everybody? Questions? Because it will come up again when we start talking about ANOVA. It will come up again when you do homework problems, take-home exam problems, where we have to assess our data.
So when I read articles, I never see anyone report their Levine's test.
The only time you ever see it reported is if it's violated.
Right, so is it one of those cases where, right, like if you're on the borderline where like one of them is significant and the other isn't, like maybe you should just kind of reconsider everything altogether? Like, are you really fine? Like, it's the same way we talk about one tail and two tail, right? Like, well, if I do it this way, then it is, and if I do it this way,
I don't think it's quite as, what's the word that we used last week? Sketchy, yeah. It's not quite as, what is it? Yeah.
Sketchy or shady?
Yeah, both of those work. It's not quite as sketchy. It's not quite as sketchy as the person who does the two-tailed test, because that's what everybody does, sees that the two-tailed test is significant at p is equal to 0.08, and they know if they do a one-tailed test, it'll be 0.04. And so they decide, oh, God, I meant to do a one-tailed test all along, right? That's sketchy, shady, just not right. This doesn't feel this. I don't think this is used in that same way. I do see it when the assumption is violated. I do see people report it from time to time, I think it makes sense not to report it if you don't violate the assumption, because the reader assumes that you've assessed all of your assumptions and you've met them unless you decide you're going to report them. And there just isn't room, in a dissertation, there's room to report all of that stuff if you choose. In a journal article or a paper that you're hoping to get published in a journal, there just isn't the real estate to give all of those details, except for when the assumption's violated. So, but that's just my experience. Other questions? Make sense to everybody? All right, let me do that. And so let's just think about, this was just a, what does that turn on? I'm going to turn on these. And so let's just look at this and take 10 or so minutes to see if we can come up with a strategy for it.
So we write on this.
Please do. You don't have to though. I'm not going to collect these. So we're doing a study, let's say that is a repeated measure study, where our participants completed a questionnaire and received a manipulation at time 1. And then we did a second questionnaire at time 2 a week later. And this could easily be a study that we do here in Burton Hall, or it could be something that we did online. I don't think that matters. It's just a within subjects repeated measures problem. And so at time 1, we have 3 dependent variables, and we have 275 participants. And then we have 2 independent variables, so we manipulated 2 independent variables for our experiment, let's say. And we've got 275 people that completed both of those. And then at time 2, for our 3 dependent variables, where we just wanted to see, maybe we manipulated some media message at time 1, and we wanted to see does that, and we assess the effect, immediately after the participant received the message, and we wanted to see, does that effect hold a week later? And so we have them come back, but at time 2, we only get 221 participants that make it back for time 2. So obviously we have some missing data, right? How would you think about how you would dummy code? I don't want the steps in SPSS necessarily, but the logic behind how you would dummy code up the grouping variable that we'd use, and then what you would test that grouping variable against, and what kind of test you would do then with that grouping variable. Okay, so let's just take 10, 15 minutes, whatever it takes to, and work on it with your colleagues if that's what, it's not a do it by yourself kind of thing.
And then testing like these ones, these would be tests. Crosstabs.
This measures time too, right? Since that's where the data get missing. That would be the one that had all the missing things out of it. All those dots. So we would actually go that one.
Are we making the assumption that folks only drop tabs and like a group of people might have showed up to take time to let's say,
Nobody did it at time 2 who didn't do it at time 1.
Okay.
Good question.
Okay, so then after we dummy coded, we would need to run time two against what we do. So grouping variables would be
If there's
No, so if this is time 1, and this is
yeah. Yeah, no, you're right. Because it's continuous and not
yeah, I just know that
manipulation.
oh yeah. Yeah, we want to make sure that there's no, I think you're
Well, I was going to say, I beat you to it.
Oh, so here we're comparing whether they're coming or visiting. Yeah.
You guys got it?
Oh, no, 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 I've never looked at it. I'm comparing this person's my group experience. Yeah. So like folks who drop out have some have conflicts. Help me understand why. Yeah, right. Because here I don't have it.
You doing all right?
Yes, sir. So there's nothing I can compare. So I was only comparing. Based on
It's a good one.
and then we use that.
Can you do all right? Guys doing all right? You guys are doing okay? So maybe.
And then with the testing that has to do with manipulation and time. I was thinking it was continuous, but yeah, we should just go ahead and do that. Yeah. That is true. But I did eat the Chick-fil-A, I was like, I can't take it. And then I was in my meeting with Dr. Kramer and I was like, I'll be back. Okay, so that does make sense. So we're so that's a good thing. So like when you don't make something, you do the ones you can.
That's awesome.
No, see.
Everybody have something? So what's the approach that who thinks to have is there a right approach? I think there's approaches that one would take. Some might be more efficient or more intuitive than other approaches. Who thinks they have a good approach that they want to share with us? What they would do?
So,
Thank you, Brittany. Thank you.
no problem. So we decided that the first thing that we would need to do is dummy code the DB for measure time 2, since that's where the missing data was. That would be the column where the stuff was missing from. And we said, of course, in the ones and zeros. And then
And how many ones would we have? How many zeros would we have?
so 0 being not missing.
Yeah.
So 221.
Right.
And
then
54
50,
ones.
yeah, good, yeah.
And then we said we would test that against the manipulation at time 1. And since they were both nominal variables, because after we regrouped it, it was nominal, or dummy coded it. And we ran a chi-square.
Yeah.
Is there steps after that? Oh, hold on, that's where I stopped.
That's where it's at?
Yeah, and somebody, pick it up, y'all, pick it up.
Anybody disagree with the logic? So we take the time 2 dependent variable, where we have 54 missing, 221 not missing, dummy code it just like we did in class the other day, and you did for your homework into a dichotomy. That would work perfectly fine. And then we run 2 chi-squares. Is that what we said? 2 chi-squares for 2 independent variables. And what would that tell us? How would you interpret that? If one of those chi-squares were significant, what interpretation would you then bring to that?
The manipulation draws people to not follow through the study.
Yeah, that would be, or there's a correlation between the manipulation and them not coming back for time 2. And so, for instance, in some of the work that I used to do in the department, a lot of stuff with politics. Not everybody loves politics as much as I think they should. And so you put students in a condition where you make them read political messages, or you make them think about political things that they maybe they don't think they have enough experience, and then you make them do that, and they might say, well, God, that study was awful. I'm not going back there. I'm going to go to the study where I can do interpersonal relationships because I know more about that stuff than I do about politics. And so it could easily be that your somehow the manipulated variable is what is leading to the missing data, and so that's how you would interpret. That's at least how I would interpret a significant, in this case, chi-square. And then what would we do with the dependent variables?
So we'd run a t-test with the dv's at time 1 against the dv's at time 2 and see if there's a significant difference between them.
Yeah, and that would tell us what? If it is significant, how would we?
Well, then it would mean that it's systematically, not oppressive, systematically, something's causing people of a certain dependent variable to not come back.
Yeah, and so if we, go ahead, Chris.
Oh, no, so I'm kind of misunderstanding that, right? So we're going to compare time 1 against time 2, right, which I think is what you said.
Yeah.
What did you say?
I said compare time 1 to time 2. Because at time 2, you don't know who's missing. You don't have the data to know who's missing unless you compare it to time 1. So you compare the continuous time 1 against the continuous time 2, and then see what's missing and how that shakes out.
Is it the same thing that Brittany said, where we're going to take the?
No, that was with the IVs. Talking about with the DVs.
But we're going to take the DV at time 1 to create our grouping variable. Is what how I understood what Brittany was going to do.
I think
Take the
the DV at time 2.
What DV at time 2? Yeah, take the DV at time 2 to create the grouping variable. Right. Okay.
Right.
And you do the same thing.
Yes.
Okay.
And then I would just compare the measures at time, the DVs at time 1 against the dummy code DVs at time 2 to see what's missing.
Yes, the grouping variable.
Yes.
Because are we? I think we're on the same page.
I think so.
Okay.
I'm hearing the same.
Chris, did you?
Yeah, sorry, I thought he was trying to compare the continuous scores of time 1 and time 2, and I was like, well, I don't understand how that would work.
Yeah, because
If
you
we're
would
using
have
it as grouping, then that's,
yeah. And then if we do find significant t-tests, that suggests that it's systematic, right? And it would suggest that maybe one of these is, if again we're doing a study on politics, maybe we ask people how interested they are in politics. And if the people who don't come back at time 2, maybe they're less interested in politics than the people who come back at time 2. And that would be sort of a reasonable thing to find, right? I'm not going to go back to that study because I hate politics. I'm not uninterested in it, and so that would be an interpretation of potentially what the mechanism is that is leading to them not coming back at time 2, or the missing data, however you want to put that. In my case, meaning the same thing. What else might we add here?
we have to run those as if statements, right? Like if you're in ID 1, then check the DVs. If you're in ID 2, then check the IDs as a t-test, depending on when those DVs appear in the survey or whatever it is you're doing.
So IV1 is just, let's say it's a trichotomy. We had 3 different conditions. And IV2 was a different manipulation. Maybe it was just a dichotomy, right? And so we would just do I would do just 2 separate t-tests, or 2 separate chi-squares to assess.
I'm just curious on the DVs, right? Would I?
DVs at time 1?
Yeah, DVs at time 1. I'm going to run the t-test because those are continuous variables. But would I have to include an if statement to run them whether they were in ID 1 condition or ID 2 condition or what? Like based on condition, because those came after the independent variable.
So you might do, if you thought there might be an interaction, it might be what you're trying, if you think there's an interaction between the dummy-coded missing data and one of your manipulations, then you would just run an ANOVA that would include the interaction term, and that would assess whether there was an interaction. Is that?
Yeah.
Yeah, and so you probably could do it with the if statement if you wanted to. I don't know why you would, if you could just run a two-way ANOVA, that would, or maybe you could do a three-way ANOVA, include both of your independent variables and your dummy-coded missing or not missing variable, and then the three dependent variables. And so you have a three-way ANOVA.
I just had a concern, I'm just thinking, we could have had some other continuous measures that we're measuring, it need not be the same one. I called them in week 1, I measure a different set of things in week 2, and I thought, once we've done the grouping variable at time 2, if it was a whole other variable, then it makes sense to compare it. But the same variable at time 1 and time 2, even with the grouping, would it, like, is it, even if I make that accurate prediction that is that the right way to go? I was just wondering that maybe, isn't that a concern?
I don't quite follow the
Okay,
concern.
so I was saying, like, we have the same dependent.
Right, so let's say you did a study where at time 2 you had a different set of dependent variables that you cared about, okay?
And we had the same data in those. To me, I was thinking, and I made that into a grouping variable, and I compared it to the dependent variable.
Brittany would do exactly the same thing as she did with this one, with the example you're giving, right?
Yeah. And it makes sense. So, for example, my DV1 is, how open are you, and my DV2 is, my DV at time 2, a week later, I asked them, how likely are you to accept something.
Right.
But if I ask them that same thing, if I ask them the same skill a week later, I was just wondering, I know.
Are you worried about sort of the person's, because they're going to, at time 2, they're going to be sort of clued into what we're studying, right? Yeah, so that's always there's always a price to be paid, regardless of design you choose. And if you do a repeated measures design, in all likelihood, your participants are going to know something about your study at time 2 that they didn't know at time 1. And but it's a price you have to pay, right?
The ones who dropped out is fine, but the ones who showed up, asking them that same question, their response may not be indicative of the truth yet.
But it's either way would be typical, right? I've seen a lot of studies that at time 2 they're asking them the same set of dependent variables because they really want to see how much decay or how long does that manipulation last. If it's a medium message, for example, is it just within 5 minutes, or will the effects last for days or weeks? But certainly, and so that's an approach that's oftentimes taken. But another approach, given a different theoretical context, surely could be a different set of dependent variables at time 2. I don't think that changes anything that we talked about in terms of missing data analysis. For me, it wouldn't. We would dummy code the variables the same way. We would have the same set of tests that we would do because we're only going to do tests with the independent variables that were manipulated at time 1 and the dependent variables that we collected at time 1 because we can't do it at time 2 because we don't have any response for anybody who's coded 1. We have no data for them at time 2, and so we can't even count the SPSS won't even be able to run the test. Is that other questions, comments? All right, so this is a nice kind of a problem that you might see on a take-home exam, or not a take-home exam, an in-class exam, or take-home exam for that matter. But put a note on this and throw it in your notes, or take a picture of it and say, think about this for in-class exam. And I'll do the same. So getting back to where we left off. The last slide, we sort of went through some of these last missing data slides somewhat hurriedly last Wednesday, but I think I got everything out that I wanted to get out, and nobody had any questions. So moving to the next topic is outliers. So we're going to first talk about univariate, or if on a single variable, and then we'll talk about and how we detect those. And then we'll talk about multivariate outliers and how one would go about doing that detection. But first, maybe some reasons why we have outliers. It might be when, back in the day, when we used to enter data in by hand, right? Nobody does that anymore. When's the last time anybody had to enter data in by hand? Did you have to do, what did you, what kind of data?
We do a pencil and paper word stem completion task, and we have to, we literally read them and then code them and then flip it into.
How come you don't have them do it in Qualtrics or?
Well, we tested it online and with pencil and paper, and it turns out there's something about the mechanical process of writing that makes it work better.
So I can no longer say back in the day, because some people still do enter data in by hand, but more and more, it used to be just, you'd have a stack this tall, and if you're lucky, you had a graduate student that would help you, or undergraduate, and say, okay, enter these in, and you can easily enter 9 instead of 9, right, when you're doing data entry, and so those kind of data entry errors can cause problems with outliers. Easy to fix, as long as you identify them, right? If you enter 99 for somebody where you should have entered 9, hopefully you catch that. If you don't catch it, I don't know what it means, but hopefully if you sort of follow the logic that I'm putting forth for this class, you would catch that at this stage, and you say, oh, 99, that's not even a possible response. I need to go back and find out what that person's actual response should be. It could be, remember I talked last week about missing data codes, where I might say minus 9999 is going to be missing data. And I might forget to tell SPSS that minus 9999 is missing data. If I forget to take that step, that number is, that's going to be an outlier in all likelihood, right? Because it's an extreme number. In all likelihood, it'll be an outlier. So another reason for outliers could be just having your missing data codes don't square with what you're telling the computer to use for missing data. It could be some kind of response error where and response, I think error is probably, but if you ask people how much TV they watch a day, and somebody says, well, I watch 24 hours of TV a day. Well, maybe, but maybe not too, right? And so it's probably a misunderstanding of the question, or somebody just not wanting to tell you that they watch 8 hours a day, which they think is a lot, and so they just go to the extreme and say they watch. So, but that could be a response error. What would be another example of a response error? Anybody else think of another example where you're getting maybe you're working on the computers. Is there still a lab downstairs? Have I asked this? Back in the day, in the lab, you'd have to go there and start the computers up at least a day ahead of time, because they'd have to update all of the antivirus, this and that. Have I told this story before?
Yeah.
Have I?
Yeah.
And so it could be that you have, if you're measuring latency in milliseconds, and that computer downstairs is struggling just to update Norton's antivirus, and you're trying to tell it to capture a keyboard click in milliseconds, it might have to add a little bit on to, it just might take it longer to get from the keyboard strike through the CPU to give a number to. And so that would be another form of response there, just because, in this case, the machine had led to the error. And then, of course, we have just the rare event where it really is legitimate but they're extreme observations. So let's say I was an undergraduate student, and you had doing a study, and you asked us our ages, and I gave you my age, and then you had everybody else's age. I would be at least 2 standard deviations, maybe a standard deviation and a half from the average, quite close to 2. From that, right? But it's legitimate, right? It's. I'm just old and they're young, right? And so it would just be that situation that one would have to make some judgments about what do you want to do with that data? Do you want to keep it, or is it in some way disproportionately having an impact on your results that you think needs to be addressed, and those would be the kinds of decisions that we'd make. So those are some reasons. Any other reasons? Can anybody else think of other reasons that maybe I don't list here? Other examples?
Once in a while, like I've noticed, like the outliers. I mean, the sort of the endpoints that the researcher puts into the system somehow can also cause like a response error.
So, for example,
like putting a text box, and so you may not get a certain kind of desired response, or if you have made an error while coding it, like 1 to 7,
yeah,
including not including
Yeah.
7, and then
yeah, and that's sort of similar to data entry error, but it could be but it's distinct in some ways as well, where it might not be a sort of a straight data entry error. It might be a coding kind of error that would get, or misclassification that gets made along the way. So some reasons, and there probably would be other reasons if we thought about it long and hard enough that we could add, but I think those are probably the most of them. So how do we detect outliers? And I give you a couple different approaches here, both of them using the same logic. It's just getting at it in different ways. One of the things we can do is just look for cases or data that is 3 or 4 standard deviations from the mean. That's a long ways, right? Using what we know about standard deviation, 68% of the observations are plus or minus 1 standard deviation. Rounding here, 95% of observations in a normal distribution are within plus or minus 2 standard deviations. 99.7% of in a normal distribution, 99.7% of the observations in a normal distribution are within 3 standard deviations. That covers just about everybody, right? Not everybody, and we'll never cover everybody, right? This will only approach 100% or 1. But let's say you look at your data and you find somebody that is 6 standard deviations from the mean. Is either above or below. That's a long way. That is a rare thing, right? However it got there. However legitimate or not legitimate it is, it's a long ways from the mean. And so that should be a cause for concern. And an easy way to do that is just calculate plus or minus. And in the example I gave, I just did approximately 3 standard deviations. So we have a mean, we have a standard deviation, and I add 3 to that mean. I add 3 times the standard deviation to that mean. I take the standard deviation times 3, and then I also take the mean minus that, and so I come up with this range. In this case, I got minus 4.5 and 11, and I just look for people who are or observations that are outside of that range. And you might not decide to do anything with those. They might be perfectly legitimate, but that's a decision that you get to make, and that you'll have to make the case for. I would say, if you have, if I was on somebody's committee and they had, well, I was working on, it was actually another project I was working on, and the company that was doing the work for us, they had Z-scores that were like 15, which means there are 15 standard deviations from the mean. No, that doesn't happen. Not as frequently as you're telling us it's happening. And so something's wrong with your data. Fix this, because it just does not make sense that, 15 standard deviations from the mean just doesn't happen. It's like the Patriots winning the Super Bowl, right? At the start of the fourth quarter, you would have made that bet. And so when I say it doesn't happen, of course it could happen. But even the age example that I gave you, if I was 110 and I was in your class of 18-year-olds, I still wouldn't be 15 standard deviations from the mean, because that's just so extreme. So that's one approach. Another approach that uses the same logic, but instead of doing this range, we just calculate z-scores for our data. Does everybody remember what a z-score is?
Standardized score.
Standardized meaning what? Standardized in what way?
That it's irrelevant the type of measure applied. All the scores can be compared because they stand on the same line.
Yeah, and so mean 0, standard deviations equal to 1. So that's when we do z-scores. That's what we're doing. We're taking our data and we're transforming it in a way where the mean becomes 0 and the standard deviation becomes 1. And the formula for doing that is, I think it's included right over here. The formula for doing that is, does anyone remember? So it would be x minus x bar. So this is your x score, and this is the mean, so xi. So this would be for person I. You take that person's score minus the mean. That sets the mean to 0, right? This part sets the mean to 0. Because if you take this minus the mean, if this person's exactly equal to the mean, this is going to be equal to 0, right? If this is exactly equal to this is going to be 0. So this first, the numerator sets the mean to 0, and then we divide by the standard deviation, which sets the standard deviation to 1. Some people don't do it. Some people just do this, the numerator, and we just call that centering the variable. We leave the standard deviation as it is. So some people just center the variable and they do each score minus the mean. That's not called a z-score. If you divide by the standard deviation, we call that a standardized score, a z-score. Some people might call it a normalized score. So we can do this pretty quickly in SPSS, and then we just look for, in absolute terms, we look for scores that are greater than, in absolute terms, greater than 3, for example, or greater than 4. And those would be considered maybe not outliers that you would get rid of, but at least outliers that you'd want to consider. Let me look at this thing, or let me look at this person and see if that score makes sense. And if it does, of course, then you're going to continue to use it and not think anything of it. If it doesn't, then you'll have to make a choice of, well, what should I do with that, with that particular value. So, in terms of the logic of doing this, does it make sense? And I'll run through how we would do it in SPSS quick, or maybe it won't be quick, but I'll run through how we would do it in SPSS so at least you can see how to do it in SPSS, and then we'll be able to move on. Fair enough? So here's some data. And using the using the two approaches, the first thing I might do is just do analyze descriptive statistics and frequencies. And let's just work with that income variable that we worked with before. And I'm going to ask for statistics. I need to have the mean, and I need to have the standard deviation. And so in this case, the mean is 13. The standard deviation is 5.5. I could quickly take 5.5 times 3, add that to the mean, and then look to see how many responses that I have that are below that value. And in this case, this 13 represents they're in the 13th category, which there seems to me that there might be a way. Does anybody know off the top of their head if I didn't want it to put the actual label here, if I wanted to put the number here, does anybody know how to do that?
If you try maybe SPSS statistics, and it goes into options or preferences, and then from that screen,
I can tell it not to put
the
labels for the tables. Because I would, if this were me, in some cases it would be nice to have, well, this is under, I have 8 people that make under $1,000. I have 20 people that make between $1,000 and $299. So in some cases it's nice to actually have the label there. In other cases, for example, this case, it would probably be more useful to have the number there. So I could tell, like, this is number 1, this is group number 2, this is group number 3, this is group number 4. And I could easily count down to I could easily count down to the groups that I needed to count down to in order to see if I had any outliers.
You just go to statistics real quick and then preferences, and then you can just, it's the first box you can check. Display
This one?
Mm-hmm.
Oh,
But you need to rerun the analysis.
Right.
right. Whoops.
So it didn't change it.
It's display labels, right? Or display names is what it should be?
Display labels.
Is there no save?
They're like a save. Yeah.
You think it's saved this time?
It's under the output, actually, not the general. There's a sub tab up there that says output,
Under options.
just right under options, in the middle.
So
Next to currency.
Here?
Tabs at the top.
The tabs where it says general and it's highlighted blue.
Yeah,
They have to
And
choose
then go to the
output.
middle to output.
got it. And this we want to be names, or names and labels. And then is there not a save, or is the save hidden down here somewhere where I can't see it?
Down the bottom.
Is it? Let me resize this. Oh.
Apply.
Ah, was that there before? Or did I resize the window enough?
I think the resize of it.
All right. And so then if I rerun that, keep your fingers crossed. What? Somebody figure that out for us, and you can school us all on how to do that. Either you'd be able to work with it this way. I I think you could recode it. Another way to do it, if I really was serious about it and I wanted to get it done quick, I could recode it into a new variable where I didn't, or I could just go in and erase that label and just have the numbers. And then, of course, it doesn't have the. So there'd be a couple different ways to do it, but there's got to be a preference that we can set. And then if we figure that out, we'll get that. The other way to do it, and this would be my preference to do it this way. So we can calculate with a compute statement, and we could do that. We could do each score minus the mean divided by the standard deviation. Easy enough to do, and we could do that with a compute statement. And just to do it, we can do, so I'm going to call this Z income. And so I need each X, and so what I need is the respondent income here minus, and then I'm just going to do mean of respondent income, right? And then I need to do parentheses around that, because then we need to do that math first before we do this math, right? And then the denominator there is just the standard deviation. And then is the formula just SD, or the function just SD? Does anybody remember? For standard deviation? Yeah, so that's the standard deviation. So I can just do SD divided by income. And then I could say, okay, which one requires more than two? Oh. So what we actually have to do here, instead of having it compute the mean, we can just take our mean from over here. 13.83. I thought it would do it that way. 13.83. So I'm going to do each score minus 13.83 divided by the standard deviation. And it might not like that standard deviation too. Yeah. And so, thank you. 5.55. 5.55?
Yes.
And so now we created a new column of data that's called Z income. So that's one way to do it, just using that formula. I don't know why you'd ever do it that way. If you could just do descriptive statistics and descriptives, and see this little thing down here that says save standardized values as variables. And I just move that income variable over there. And when I run this procedure, it's going to also create a standardized version of that. That's going to be exactly the same as what I created. So that would be the way you would do it, unless you just like to, I don't know, do it some other way. But if we look at that, we have two rows of data, or two columns of data here that indicate the Z-score for our income variable. And then what I would do is just do I would just do analyze descriptive statistics and frequencies. And then we don't need the frequencies for the income. We need the frequencies for the standardized income. We could use either one of them. I'm just going to use that one. And we can see that our lowest value is minus 2.3. So how would we interpret that? How far is that from the mean?
2.3 standard deviation.
Yeah, so you'd interpret that that's 2.3 standard deviations below the mean. Is that an outlier or not? What's that? Yeah. So I would say, unless it's greater than 3, I probably would not spend much time on it. If it's maybe getting close to 3, maybe you want to look at it. But something that's in the mid-2s or minus 2.3, I would not worry about it. And then the max value is 1.65. And so, again, nowhere near 3. And so it doesn't raise any red flags for me. Does that make sense? So everybody will be able to look through their data and make this same calculation. And so the question, just bringing it back up again, would you do it on the individual items, or would you do it on the sum scales or the average scales? Chris, because you brought it up earlier, how would you do it?
Well, it depends on what I'm looking at. But you most likely run it on your sum scales.
Yeah, I think I would too.
But I would probably run a frequency to make sure I didn't have any values that I screwed up ahead of time on those items.
That would be good because for the individual items, you could easily have done 9, 9 instead of 9. And you may not, well, my guess is that would probably show unless you had a lot of items, but I probably would not hurt to do the frequencies on the individual items before you sum them up, just to see if you somehow did data entry error there, or if there was anything that looked out of the norm. But I think in general, I probably would use the summed or the averaged composite of all of the items when I did my missing data analysis. Does it make sense? Questions about univariate missing data or univariate outliers?
So going back to the clean data and this, if you look at the variable, the only thing I'm worried about is if you have an item that's really that's causing the issues. It's one item that's causing the issues.
Everybody entered or gave you 9 for it, and lower values, 1s or 2s or 3s for all the other one, and
yeah, it's just not rubbing people's right way or something. It's that item that's actually pulling the weight and not the variable.
yeah. If everybody answered that way on the items, I don't know that it's a problem with an outlier. It's just that that's how they're responding to that question.
Right. Well, normally, I'm thinking the item's probably going to get dropped when you look at alpha analysis or like a factor analysis and stuff. But in terms of this, if we're doing this pre-doing those things, I'm thinking the items are more beneficial to look at, so we can screen out items that aren't lining up with the others.
And by not lining up, just meaning that people have different responses on them.
For some reason, it really hit people differently than the other items, right? So if I have 10 items, I measure your anger, and one item is causing these outliers to occur, right? Where people are really high on this, but they're not on the other items.
But then it wouldn't be an outlier almost by definition, right? Because if
or just some people are. Maybe that's
Yeah,
a big item
yeah,
missing
yeah, that's a good point. Yeah, so maybe, and that would be something that you would. So you again, let's say we took the approach that we wanted to work with the composite. We look at the composite and we see that we have a couple people or several people, whatever the number is, that are extreme, they're outliers. Then I might go back, I'm trying to figure out, well, why is it that? Then I might go back and look at the items and say, well, for item number 7, all of these people answered on the extreme, where everybody else for that item tended to be much less extreme. And that's the thing that's leading to them being classified as outliers. And then you'd have a decision to make about what are you going to do with that? Are you going to drop that item totally? But does that make that might be the thinking.
Start with the variable and work back to the items if there's an issue.
But if you wanted to work with the items too, you'd probably come to the same conclusion, my guess is, right? So it's not I think I might, just because I tend to be lazy sometimes, I might start with, I'm going to build my composite. I'm going to see is there any problems with the composite? If there's not, that doesn't mean for certain there's no problems with the items. So maybe your thinking would be the more conservative approach, I think, where I'm going to look at all of the items, see if there's any problems there, and then I'm going to look at the composite. That might be just a more, I don't know, more thorough makes it sound like I'm not doing my job, which may or may not be the case. I think in most cases they would line up. But so just thinking out loud and not at all sort of embarrassed to explain how I would do it. There might be other approaches that would make more sense, and certainly in some contexts. So if you decided for the homework you were going to look at the items, I wouldn't say, what are you doing looking at the items? It could make a lot of sense in some cases. So does that confuse more than help, or help more than confuse? It helps more than it confuses? I hope so. I'd like to see a few more people nodding their head. Oh, good, I feel better now. North and south. So we are good on univariate outliers. By the way, that's the easy one. As you would expect, when we start looking across all of our variables, it becomes more complicated, and it's not as straightforward as if this last 5 minutes was a straightforward conversation. But it's certainly less straightforward. So it could be that we have. And I'm surprised that I don't have a slide in here. I should have put another slide in here where I would talk about the case where we could look at scores on a univariate or data on a univariate basis and not find any problems at all. But when we start looking at variables in combinations, we might find some extreme cases. And that's where the multivariate outlier detection would come into play. And so an example might be looking at I could look at on a univariate basis how much time people say they spend a day watching TV and how much time people say they spend working. And so I'm either working or watching TV. And on a univariate basis, you might not find any problematic no outliers. But somebody who says they watch TV, I guess it would be possible. Maybe they watch TV for a job. But I watch TV 12 hours a day, and I work 12 hours a day. So you might not, on a univariate basis, 12 hours probably for TV watching is a bit extreme. Although I think my dad, who's retired, always has the TV blaring in the background, pays some attention to it. The thing is on certainly more than 12. So he might give you a number higher than 12. So on that sort of univariate basis, no problems. But if you look at, you sort of cross those two, here's somebody who both watches TV 12 hours a day and works 12 hours a day. That's really unusual when I compare that to everybody else. And then again, what do you do with that would be a researcher decision that has to be made. It doesn't mean that you delete them automatically or get rid of them from your data set. It would just alert you to a unique situation, and then you could make some decisions about what to do with that unique situation. So we're going to do this fairly common statistic invented by an Indian mathematician with the last name of Mahalanobis, and it's we're going to calculate a Mahalanobis D2, and it's pretty. If you sort of think about it like a z-score, except for it's a multi-dimensional z-score. And it's looking at this multi-dimensional space instead of this unidimensional space that we're looking at with the standardized z-score. And so we're going to look at, well, how do you calculate the Mahalanobis score, and then what do you do with it? And that's what we'll talk about over the next few minutes. A couple important notes. It's a real sensitive test. And so I would tend to only look at cases or rows of data where the p-value is less than probably 0.001. In my experience, it's sensitive enough that you'll have some people that will be p will be less than 0.05, but greater than 0.01, and they're probably not going to be they're probably not going to be a source for concern. So for me, if it's not below 0.001, it's my experience is that those cases are going to be just fine because it tends to be a sensitive test in that way. And so just a couple other points. The d-squared follows the chi-square distribution with degrees of freedom equal to the number of variables included in the calculation. So what we're going to do is two steps. First step, we're going to calculate the d-squared. And then the second step is we're going to calculate a probability that's associated with a d-squared that's that large given some degree of freedoms, given some number of variables. And all of the variables that we're going to be looking at will have to either be continuous or metric. So thinking about levels of measurement, they would be either interval or ratio. So they have to be either interval or ratio or dichotomies. And so if you have a nominal variable, you would dummy code that into dichotomies. And we talked about dummy coding early on, maybe even week 1 or week 2. So far, so good? So I'm going to let you sort of follow through these steps in your notes. I'm going to turn to SPSS and run through these steps in SPSS that you see here, and then eventually we'll get to this screen, which is the only one that requires maybe a little bit of explanation, and then another screen where we're making that calculation, and then the last screen where we're doing some sorting. So here is for the video how I would calculate the Mahalanobis d-squared. So let's say we're interested in some of the same variables that we worked with last week, and then maybe a few other variables that are in this data set. And so the way that I'm going to have you calculate the Mahalanobis is under analysis, regression, linear. So I know this is sort of jumping ahead because we're not even talking about regression yet, but we're going to talk about regression starting either later today or next week. But this is just a point and click thing that's pretty straightforward. So we're going to do linear regression. It doesn't matter what independent or what dependent variable I use because the Mahalanobis value is calculated based only on independent variables. So it's invariant to what dependent variable you use. In this case, I'm just using their ID number, which is not a nonsensical dependent variable, but it doesn't matter for the calculation that we're doing here. And then I want to use whether the respondent is male or female, which is a dichotomy. I'm going to use those same 4 variables that we talked about last week, which is how warm or cool the respondent feels towards different groups. I want to use their age. Let's say that these are the variables that I want to use in an analysis that I'm working on. And then I also, because I've mentioned it a couple times, I'm going to use how many hours of television they watch per day, and then I guess just for the heck of it, let's put in education. So I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 independent variables, and so think back to the screen that I just had up there. My degrees of freedom are going to be equal to 8. Okay, so remember that when we get to calculating our probability. And so the only other thing that we need to do is do save, and then save, and then if I can get the box over here, one of the options is under distances is Mahalanobis. Is there an OK here that I need to I think there's a confirmation box that I want to. So maybe. If I hit enter, it'll do it.
I don't know.
What? Paul, what? Do what?
There's a continue box, I think with enter.
So let's cross our fingers and hope. Well, we can do this, right? We can do save, and it stayed, right? So we're good. So and it all has to do with the resolution of the screen that I'm working with, and so usually there'd be an OK button that you'd press, but enter works just fine. And that's all you need to do. Press OK. The output is utterly useless. Don't look at it because our dependent variable was just their case ID number, right? So don't even look at that output. The output we care to look at, though, is the output that was generated in our data file. And if we look across our data file, we'll see that we have a new variable called MAH_1, which is just the default name that it gives for the Mahalanobis. Why is it missing in some cases? What's that?
Is it the mean? Or it's like at 0 point?
I don't think so. There's another reason we talked about last week. What do we do when?
Oh, because it's excluding any data that's missing.
Yeah, good. Yeah. So in this case, it's looking at our dependent variable and all of our independent variables. And if it's missing, so we could go across for participant number 1 here. It was missing one of those 8 independent variables. I assume it's not missing the case ID. If it was missing the case ID, it would exclude it too. But I'm assuming I got a case ID for everybody. So it was missing one of those 8 independent variables. It can't calculate anything. So it list-wise deletes that person from our analysis. And so that's why that person, that's why we have the missing data here, because those are all, they're missing on one of those variables. And this, does that make sense? So what time do we take a break? 4:30? Is that what it usually is? Yeah, so let's take 15 minutes and we'll come back at 45 minutes after the hour or thereabouts. And we'll finish this calculation as I shut off the video.
Yay. Sorry, I don't know why I got that excited about that.
I was sort of excited that I remembered, but